All right. Welcome, everyone. My name is David Janes. I'm a professor here in ECE and also co-director of our Semiconductor Degrees program. I'd like to welcome you to today's event, which is triple listed. It's a Semiconductors at Purdue Distinguished Lecture. It's a SSA, Semiconductor Student Association Distinguished Lecture, and I think first and most importantly, it's an IEEE Distinguished Lecture. So I'm going to kick it over to IEEE Student Chapter to actually do the formal introduction.
Hello everyone, my name is Al Sultanbek. I am the president of the Purdue IEEE chapter, and you're about to hear from Dr. Tony Yen, who is the vice president and head of the Technology Development Center at ASML, a IEEE distinguished lecturer of the Electron Device Society, and also a Purdue alum, and most recently a distinguished adjunct professor at Purdue. Dr. Tony Yen.
Thank you. Thank you for the introduction. Good afternoon. I'm so happy to be back here. And this is going to take an hour, but I crammed a lot of slides in it because I like to give you as much as possible within the next hour. So without further ado, let me get started. Okay, so today's lecture is about EUV lithography, its history, its current status, and the technology roadmap. But before talking about EUV, I'd like to say something about photolithography itself. So my first slide is the history, the invention of photolithography. Okay, the photolithography was invented in the mid-1950s at two places, Bell Labs, by Jules Andrus of Bell Labs and by J. Lathrop and James R. Null of a U.S. Army laboratory independently. Okay, but I'm going to focus on the latter because the story is a bit more colorful. So the inventor's task was to fit a radial proximity fuse into a mortar shell. You know, the mortar shells are not very big, right? So this whole circuit, first, what is a proximity fuse? A radial proximity fuse, thank you, is a cheap radar system. The cheap radar system would cause the bomb to explode in the vicinity of the target, so to increase the striking probability, okay? So they need to put that thing in the mortar shell. And to do so, they have to shrink the size of the germanium mesa transistors. In those days, germanium mesa transistors, germanium, not silicon, okay, were the typical transistors for the electronic circuits. And the mesa had been, up to then, defined with a drop of black wax. So that wouldn't work, right? You need to get smaller. So they were thinking about, okay, we have this Kodak photoresist, which was for another purpose, but say, hey, let's take this over and use it for photolithography. So Kodak photoresist, and how did they do lithography? They ran a microscope in reverse, okay? What does that mean? That means they put their sample here, and then you do the X, Y adjustment to do the overlay, to do the alignment, and then put the mask here, okay? This is where normally we put a Polaroid camera here and to take a picture, right, of the sample. But instead of a Polaroid camera, you put the mask pattern here, and then here's the filter. The filter is a red filter, right? So when you're doing the alignment, you want to slide in the filter so that the wafer doesn't get, that's a sample, sorry, not even a wafer, it does not get exposed. So after alignment, everything is done, you pull out the filter, and then, of course, the white light goes through, and then this sample gets exposed. And that's how photolithography was done at the invention, okay? What was the dimension? Well, the die size was 1 millimeter by 1 millimeter. The mesa size was not stated in the article, but this is a bipolar transistor. So the collector contact is on the back of this die, and then you have the base contact and the emitter contact. These contacts were of 0.1 millimeter by 0.25 millimeter. gigantic by today's standards, but back then that was a small, very small dimension. So great, they made the transistor, and the project was done. And then what happened? J. Lathrop joined Texas Instruments in 1958. And you know what happened at TI in 1958, right? Kilby invented the integrated circuit. And this guy worked with Kilby for the next 10 years until he became a professor at Clemson. So he was at TI working with Kilby for the next 10 years since 1958. And we could all guess where the other guy went. James Knoll went to Fairchild in 1959. In that year, Bob Noyce invented independently the integrated circuit at Fairchild. So great, right? Both inventors of photolithography went to work on integrated circuits. Okay, so this is true story, and it's even a bit romantic. But what happened after that is less romantic. Lithography in the 1960s and early 70s was mainly contact and proximity printing, meaning no lens. You put the mask right on top of the wafer, you turn on the light, and then get the exposure. Okay. So first was contact lithography, which means the mask is in close contact with the wafer. And the exposure tools were called aligners back then. Why? Because alignment was more important than resolution. Okay, you need to have good alignment, of course, in microns. So those tools were called aligners. And this is one from Casper Instruments. This was a company from the United States. They were the kings of contact aligners. Okay, until the king is dead, and long live the king. This guy. Okay, so Canon made a few years later made a better machine. Not only does this machine do contact alignment, it also did proximity alignment. Proximity printing. What does that mean? So, when the wafer is in contact, when the mask is in contact with the wafer, you do the alignment. You rub against each other, right? Generating particles. So in order to minimize the number of particles, you pull the wafer away from the mask a little bit, creating a gap. That's called a proximity printing. Okay. And so for proximity printing, Canon was the king, okay, displacing Casper Instruments until the king is dead. Long live the king. But first, before that, I have to tell you a little bit about photomask. The photomask in those days, mask making in those days was a two-stage process. Right. The two-stage process consisted of the reduction camera and the photo repeater. Reduction camera reduced the original design by 10 to 40x. And then the photo repeater, and the end product of the reduction camera is here. This thing is called the reticle. Okay. Nowadays, reticle and mask are synonymous, not in the early days. Reticle is something that would go into the second stage. This is called a photo repeater. Reticle sits here, and then the mask comes out here. And this is a 10x further reduction. This number doesn't change. It's always 10x. Okay, when reticle is this big, and it reduced 10 times to the size of the circuits on the wafer, because you would take the mask, right, and do contact or proximity printing. So the size will have to be the same, the feature size have to be the same as those on the wafer. So this was the David Mann, a guy called David Mann, and Mann's 3600 photo repeater. By then, his company had been bought by GCA, so it's GCA is another American company, so it's GCA's Mann 3600 printer. And this is the IC layout, right? IC layouts were first put down on a thing called a Rubylith. Rubylith is this two-layer thing. A mylar, on top of it, is this red gel-like stuff. So it's a two-layer film, and what do? You take an X-Acto knife and cut out and peel off the red layer to create a circuit. Beautiful, right? This is a great artwork. And then this thing goes into the reduction camera, okay? Now I have another picture. This is Rubylith right here. And this is one of the layers of Intel 8088 microprocessor. This year was 1978. Look at the big smiles on those three guys. Andy Grove, Bob Noyce, Gordon Moore. So happy, in stark contrast with what Intel's experiencing today. Okay. No, I'm serious. Let's hope that Intel will get back to its former glory. That's your job. Okay. All right, so this was mask, and then mask is made, and do the contact printing. And so some physics, let's look at an example, right? This wavelength is 400 nanometers, coherent light coming down on a slit. The slit width is 4 micron, and what happens? So you place the wafer, right, below the mask at a distance z, and then what happens, right? You get the aerial image. The intensity, that's the field squared. If the gap is 1 micron, you get the gray curve. If it's red, it's 5 micron. If z is 5 micron, you get the red curve. There's 10 microns is the blue curve. As you can see, that you cannot control the critical dimension very well unless, right, you can control the z direction. You can control your wafer stage without any variation. Every time you put the wafer in, it's always 4 micron, always at 5 micron, but that's not possible, right? So there's always variation. Even the wafer is warped, and then you're always fighting this problem. So this is as best as they can do, and this is a 4 micron slit. Now, if we used projection printing, if you put a lens between the mask and the wafer, then this is the kind of a aerial image that you would get, right? A lot better than these curves. This is red is on focus, blue is plus minus 5 microns defocus. So you can have a uncertainty or variation of 10 microns, and then your CD, your critical dimension, will still be okay. Okay? That's the advantage of projection printing. In proximity printing, you're fighting diffraction. In projection printing, you take advantage of it. Okay? So, and then what happened, of course, as Ronald said, king is dead, long live the king. We have the first commercially successful projection imaging scanner, 1973. This thing was made by Perkin-Elmer, and the model, what the machine's called, the Microline. Microline had many models. The first one was called a Model 100. This is a unit magnification reflective imaging system with an annular slit. So the whole thing was very simple. The whole imaging system consisted of 2 mirrors, 2 concentric mirrors, okay? And then you have the mask, and you have the wafer. And the imaging is done through this slit, so you have to scan the mask and wafer. But actually, you have 2 separate things here, but they're actually GANed together with a shaft, on a shaft. That's below this graph. You know, you do this, right? So the whole thing is very robust. You scan the mask, you get the image on the wafer, like this, right? In and out, in and out. This is also, of course, the mask is still made by the 2-stage process, because this is a 1x photolithography, okay? This is just another picture of the optical system. 2 mirrors, you can see this is the mask, and this is the wafer. This drawing is without the prisms, okay? So they're like this. But in reality, you get 2 prisms here, so that now these things are scanning in the same direction. There's this special distance, H0, at which the aberrations are minimized. Okay, so there's this nice distance from the center. That's called H0, at which the aberrations are minimized. So your slit is at H0. Okay, this is specific and it can be calculated. And the first of these machines were sold to Texas Instruments October 26, 1973 for $95,000. So cheap. I mean, today's it's right, much more expensive than this, but this was considered expensive compared to the proximity and contact printers. Okay, but look at what it did to the Intel 88 microprocessor I showed on the previous slide. The yield, right? The device size is 0.2 inch by 0.2 inch. Contact printing yield is only 20%. Microline yield, 60%. Wow! So those machines sold like hotcakes. Okay, and this is what kept Moore's Law going for some time because of this projection lithography, the 1x projection lithography. Okay, and then what happened since then? Okay, so they were a king for a few years until there was a new king, of course, and then wafers got bigger, right? Features got smaller, so you need better resolution, and Microline couldn't provide it because this simple two-mirror optics has a numerical aperture of 0.17, very small. So how do you get better resolution? First, I have to tell you this formula. Now, in photolithography, if you only want to remember one formula, remember this one. Okay, the minimum half pitch is equal to K1 lambda over NA. Take Ronald's class; he'll tell you how to get to this, derive this formula. So, and this is the numerical aperture. Okay, is defined as N. N is the index of the liquid. In the air, it's 1, of course, but we also later we had immersion lithography, so N is the index of water at 193. I'll tell you this later. Times the sine of the half angle here. Okay, so NA is index times sine theta, and minimum half pitch is K1 lambda over NA. Now K1 has a lower limit. Okay, can be as small as you like. The lower limit of K1 is 0.25. You can't get smaller than that in one go. You can do multiple exposures to get a smaller half pitch, but in one shot, 0.25 is the lowest one. So now, I can tell you a bit about this formula. This formula is related to this spot. This spot is called point spread function. I need some water. Why is it called a point spread function? Let's say your mask consists of only a pinhole. Are you going to get a dimensionless spot on the wafer? No. You get something like this. Okay, you get a spot, but the spot has a finite size, and the size is equal to about 1.22 lambda over NA. This is called a point spread function. Of course, you want to get a smaller spot to get better resolution. You increase the NA, or you lower the lambda, or you work on K1. Okay, and this is what happened since the microline, this 1X thing. GCA, another American company, came out with a 4800. It also has something to do with David Mann because they call that machine Mann 4800, right? It's basically a takeover of the photo repeater concept, but this time you step it directly on wafer, right? Rather than making a mask, you basically take over the reticle and you put the patterns directly on the wafer. So this is a stepper, Mercury G-line stepper, operating at 436 Mercury G-line. That's one line in the spectrum. And then we went on to Mercury I-line, right? Reducing lambda, get better resolution. And then KRF, that's a excimer laser, K-R krypton fluoride excimer laser lasing at 248 nanometers, further reducing the wavelengths to get better resolution. And then we went on to 193 nanometer, a further reduction in wavelength. And then finally, well, we ran out of deep UV wavelength spectrum with significant output. So we started to work on the NA, and we put water between the last element of this lens and the wafer to gain a factor of N. And what's the index of water? Can anybody tell me? Okay, that's all right. It's 1.33 in visible wavelengths, but at 193, it's 1.44. Okay, so with that, we're able to achieve a NA of 1.35. And then, of course, finally, we changed the wavelengths to 13.5 EUV wavelengths, right? So this is the history of optical lithography until the EUV happened in production. And now, I want to tell you why we started EUV so early. So let me just show this. EUV development started in the mid-80s. Now, why so early? I mean, you got all this to go. Well, that's not how people thought in the mid-80s. They thought that this optical lithography would end here because the excimer lasers, they were there, but not the line narrow ones for lithography, okay? And also, people didn't think that the NA can go to 1.35 because the larger the lens you make, the more aberrations you would introduce, right? So if you have aberration, now this is just an example, this is a astigmatism. And what if this lens has astigmatism, and then this red one would be the point spread function instead of the blue one? So you got a fatter point spread function. So that defeats the purpose, right? You're going to increase the NA, but your point spread function also gets bigger. You're not gaining any resolution, right? So people thought, optical lithography only had at most a decade to go. Let's work on the next generation lithography technologies. And EUV was one of them. EUV was actually the last one among a bunch of next generation resolution lithography technologies. And this was about 1985, in the early to mid 1980s. Okay, so last slide on optical lithography. I want to show you the complexity of this immersion lens at the NA of 1.2. This was not even the last one. This was the first one that went into production. Okay, and the second one was 1.35. But even the 1.2 NA lens, this was, by the way, this is actually an example. Okay, this is not an actual design, because actual design, ZEISS doesn't reveal actual design, but this is an example. This was something close to the actual design that they put in a US patent application. Look at this. Look at this. How many lens elements are there in this lens to produce this nice, right, aberration, almost aberration-free NA equal to 1.2 immersion lens. Not only there were lenses, there were also two mirrors. Okay, so this is really a very complicated design, but it was needed to get you the NA equal to 1.2, and of course this lens would sit here, right? We have two stages. This is the twin stage ASML concept. You always have two stages. So all the alignment and metrology can be done on the side before the water is introduced, right? So the alignment and metrology can be done in the dry mode. Here is water, right? Water is here, but once water is introduced, you only need to expose, okay? Because otherwise it'd be more complicated if you have to do alignment underwater. Okay, that's already 25 minutes now, but I thought that was good for me to introduce this, to give you the background on photolithography. Now let's go into EUV, okay? Let me give you a simple sketch of an EUV exposure system. Of course, this is not right. It showed only 2 mirrors. In fact, in reality, we have more mirrors, but it's good to illustrate what I'm going to talk about. This is the mask, and this is the wafer, and this is the NA angle, just like optical lithography. NA is defined sine theta, N is now 1, right? EUV 13.5 exposures need to be done in vacuum, so there's no water. So N is 1. This is mated to a illuminator. The illuminator will give you different light from different directions to shine on a reticle to optimize the performance of the aerial image. Okay, and you scan the reticle, and now it's also called a mask. Now they're synonymous. And then you scan the wafer at the same time, and then this is how an EUV system works. Okay. Now, one thing, at 13.5 nanometer, of course, light gets absorbed immediately when it goes into a medium, right? So the optical system is entirely reflective. No lenses, all mirrors. And how do you get the mirror to reflect? Because the index at 13.5, if you take Ronald's course, he'll tell you, it's very close to 1. Okay, it's 0.9 something. So how do you get the reflectivity? You cannot with only one layer. You need to build up the constructive interference bit by bit until you reach, let's say, a 70% reflection. So this is the a multi-layer reflector interfering at every interface. You have reflection, right? So all these reflections interfere constructively to give you a reflectance or reflectivity of about 70%. And this is a TEM micrograph. You cut it up about 280 nanometers, of molybdenum silicon bilayers, okay? And the silicon layer is about 4 nanometers, and the dark layers, molybdenum, is about 3 nanometers. So the whole pitch, we call it the D-spacing, is about 7 nanometers. Okay, that's how you get the reflectivity. Every surface in EUV lithography, including the photo mask, okay, which is one of the surfaces. And this is a lens, one of the elements in our 0.33 NA projection optics. You see the face of the engineer in reflection, and this is invisible light, of course, and that's not some metallic surface. This is the multi-layer surface that you're looking at. But invisible light, it looks like a metallic surface. Okay, this is one of the mirrors, and of course it's not round. It doesn't have to be round because this is reflective optics, right? You can't have the round mirror because there's obstruction. So you only need, light only goes through part of this round surface, so we might as well cut it out and then make a mirror, which is still rotationally symmetric. But the mirror is only part of the rotational surface, okay? Symmetric surface. Of course, it's a sphere. It is not spherical. This is not a spherical surface. Every single element in the optical element in EUV, in the EUV optics, projection optics, is aspherical. Okay. Now, and what's the tolerance? The tolerance is very tight. It's less than 30 picometers from the design surface. Okay. This is the introduction. So when did EUV happen? The first paper on EUV lithography in the US was given in 1988 by 2 fellows from Lawrence Livermore National Laboratory, back then still part of the University of California. Now they are independent. Andrew Hurlick and Lynn Seppala. And they proposed X-ray reflecting masks and laser-produced plasma as the light source. Lawrence Livermore Laboratory, back in those days, they were very good at multi-layer mirrors. So those two fellows thought, gee, why don't we apply the multi-layer mirrors to photolithography, right, to improve resolution. So that's how it came about. This was the first paper they wrote, and this was 1988. In 1989, Andy Hurlick and co-workers actually made a mask, multi-layer with absorber, gold absorber. We don't use gold now, but it's close to what we use today. And they actually made a mask. This is a SEM micrograph. And the source they proposed was a plasma source peaked at 13 nanometers, very close to what we use today. Today is 13.5, okay? So very good, talking about almost 40 years ago. And then 1989, the same conference, NTT Japan also had a paper on EUV lithography, and by Kinoshita and co-workers. Back then, EUV lithography was called everybody called it soft X-ray lithography. In fact, 13.5 nanometer is in the soft wave regime, soft X-ray regime. Okay, but the name got changed in the 90s to EUV lithography because these guys were competing with the 1X proximity X-ray lithography for funding. So they changed their name, because otherwise, right, the government said, I'm going to give it to you. Well, no, we have a different technology. And then they had to change the name to EUV lithography. Okay, so Kinoshita-san, this was his setup. Again, two-mirror thing, reflective mask, and then he produced 0.5 micron lines on PMMA. It's a photoresist, X-ray photoresist back then. But this wasn't his first publication. He first published his first results in 1986. Okay, so he was in fact the first one, predating the U.S. folks on publishing on EUV lithography. This was 1986, but the U.S. folks did not know because this was published in Japan at the Japan Society of Applied Physics. The whole thing was in Japanese. But anyway, it doesn't matter in what language, he was the first one. Okay, so a year later, 1990, Bell Lab also published their results by a group of people. Their results used, again, a two-mirror optics, but they used a transmission mask. This is a membrane mask, okay? We don't use membrane masks today. We actually use reflective masks like the Japanese and Andy Hurlick. But Bell Lab's results, nonetheless, back then was a membrane mask. But they had the best results. They generated the best results. Pitch 100 nanometer, okay? Unheard of back then, okay? And to do that, they actually had to open up this aperture to an NA of 0.16. This thing was rated at NA of 0.08, right? So why was it 0.08? Because if you open it up, there'll be a lot of aberrations, but they were printing lines and spaces, features only in one direction. So as long as the aberrations are small in this one direction, you open up the aperture and get better results, right? So that's what they did. So they opened up the aperture and printed these lines, beautiful lines at 100 nanometers. Of course, in the other direction, you probably won't get the 100 nanometers lines, but that's okay. You only need to show this in one direction, okay? So this was the early days, right? Now came 1997. The next phase in EUV development, EUV LLC. So if the early days researchers were gangsters, this was organized crime. Intel, led by Intel, the EUV LLC was formed with members AMD, IBM, competitors of Intel, but it didn't matter because this was pre-competitive, right? So led by Intel, EUV LLC was formed, and they collected money. They sold shares. Each share was $5 million. So Intel had many shares, and AMD, IBM, Infineon, Micron, Motorola, they had at least one share, okay? And this money was pooled and farmed out to what's called a virtual national laboratory. The virtual national laboratories basically consisted of three laboratories, Lawrence Livermore, which we talked about before, Sandia, and Lawrence Berkeley National Laboratories. And these people carry on the actual work. It is this time that ASML joined the EUV LLC and started to work on EUV lithography. Okay? Now, EUV LLC ramped down in 2002, 2003, and ASML ramped up. So in 2006, we shipped 2 machines. These are called alpha demo tools, ADTs, to 2 places, one to Albany, New York, and then the second tool went to Leuven, Belgium, to imec. All right. These photos were from our partner imec. The machine was installed. First slide, 2007. A tool was accepted in 2018. And this is a discharged. This tool had the light source discharged plasma, produced plasma light source for generating EUV light. We don't use this anymore, okay? Because this source is basically not viable for high volume production, okay? Now, and then what happened after the 2 ADTs, we started the second phase of EUV development by churning out 6 development tools. These are called NXE platform, NXE 3100. 1, 2, 3, 4, 5, 6. It went to 6 places. The second tool went to imec, and Intel, Samsung, Hynix, Toshiba, all had a tool. And TSMC, where I was, received the 6th tool, the last one, okay? And this picture was taken by me, summer of 2011. 3100 arrived in Taoyuan International Airport in Taipei. And then 4 months later, this tool was almost completely installed inside the R&D fab of TSMC in Hsinchu. Okay, so what happened was that we were working on this tool. The original intention was to use EUV lithography for 10 nanometer generation. Of course, it did not happen, but this is one of the early shots of a metal layer, right? With pitch 46, this is a 2-dimensional metal layer, because in the early days, we thought that EUV would work. We would continue with a 2-dimensional design, which up till then was 2-dimensional. The metal layers were all 2-dimensional. Well, EUV didn't make it, and the design was changed starting N10, right, a 10 nanometer node, to a 1D design. Okay, so today it's still all the metal layers are 1D, because EUV did not happen in time. Now, fast forward by 11 years, today with the high-NA machine, EXE 5000, and this is the kind of a 2D structures we can print. Look at the pitch period, 22 nanometers. This was 46, okay? So we improved by almost 50%, all right, for resolution, okay? All right, now this is a chronology of EUV lithography development at TSMC, led by me, and this lasted 10 years. And then I joined ASML. The development continued for 2 more years, and then in 2019, EUV went into production. We see from TSMC, this was a paper published by TSMC in IDM, December of 2019, saying that EUV has now gone into production. And this is just an illustration of EUV patterning of a metal layer compared to a 193 multiple patterning with 193 immersion lithography. I means immersion. Immersion 4P4E, that's TSMC's lingo for quadruple patterning, 4 times lithography and 4 times etching. And this is EUV 1P1E, 1 photo, 1 etch, right? This is very nice. So EUV has much better resolution than optical lithography. Yes, you could achieve the same structure using multiple patterning with 193 immersion, but look at the fidelity, poor and good, okay? And then, of course, ASML, starting with ADT, right, the 3100, and then we went on to market the 3300B. Those were late stage R&D tools, and then of course, and then we had 3400B and then 3400C. In 2019, we started to ship the 3400Cs, and these were production tools, of course, R&D and production tools. And then in 2021, we brought out 3600D, again, production tools for the 3 nanometer node, okay? So this was the history in a nutshell. So let's talk about the current status. The current status, EUV lithography is now used for patterning logic and DRAM integrated circuits, right, using the 0.33 NA machines. But I also want to talk about the 0.55, the high NA EUV. So let me go. This is the latest model of 0.33 NA EUV, still the low NA. This is called a 3800E. This is the model, right? The productivity is at 220 wafers per hour. And this is used to pattern the 2 nanometer node and the DRAM circuits. Okay, so just want to tell you the overlay capability, overlay, right, layer to layer alignment. This is the number. If you stick to one chuck, wafer chuck, if you don't change chuck, you put the wafer back to the same chuck, your overlay is very good, about 0.6 nanometer. This is not just the 1 point, right? This is, look at this. Every field is 49 points, 76 fields on a wafer times 12 wafers. That's the number. And this is not just the mean or 3 sigma. This is mean plus minus 3 sigma. This is the whole thing. Okay. But if you use both wafer stages and you mix and match with other machines of 3800E, this is the kind of number you get. Still less than a nanometer. Okay. So pretty good. Now, this is on pristine wafers, right? Used for machine testing before the machine goes out the door. What about on real wafers? Well, on real wafers, also very good because real wafers are warped, expanded during processing, but we have ways to control, overlay by several means. The wafer stage, the lens elements can move, even the mask stage can move, okay? They all work in synchronization to minimize your overlay error. So what can you do, right? This is already close to 1 nanometer by only making these mechanical movements. But we can do better. We have OPC. We have other holistic lithography. So in the end, we can still take the overlay to less than a nanometer, even on a production wafer. Okay. All right. So this is what we can do. And how many machines have we sold? Well, this is a somewhat old slide. By the end of last year, we sold about 270 0.33 NA machines that are all in R&D and production. Okay. This was by the end of last year, and we've gone over it. Of course, right now the number is over 300 now. And how many wafers can they print per day? Well, this was, again, end of last year. The number is about 3,000 to 3,500. Okay? This is the kind of wafers that you can churn out on a EUV machine per day. Okay, so now this was the low NA. We call it low. Marketing doesn't want me to say it's low NA. It's 0.33 NA. But this is the workhorse today for leading edge, making leading edge chips. I'm sorry, I'm a little thirsty. What's next? Next is the high NA EUV machine. The numerical aperture is 0.55. Okay, because we would like to continue with Moore's law and getting better resolution. So starting 2014, we started to work on the high-NA machine. First, we had the optical designs, anamorphic design, and then we had the module manufacturing, and then we had the module integration, and then, of course, testing. This is in Veldhoven. This is the wafer stage, right? This is the reticle or the mask stage here in the United States in Wilton. All the reticle stages are made here in the United States in Wilton, Connecticut. And we assembled the first machine in 2023, I think, yeah. The summer of 2023, we put the first machine together, and then this is the joint lab with our partner imec. We have a machine there starting 2024. But one thing, I don't have time to show you one slide. This is the last mirror. This mirror faces the wafer, okay? This is the biggest mirror on the 0.55 NA machine. And what's the dimension? The dimensions is just over 1 meter in diameter, okay? And with a figure control of 20 picometers. That means the deviation after polishing from the design surface is less than 20 picometers, okay, throughout this 1 meter diameter. Okay, so now this is the first machine that went to Kayvon's former company, Intel. By the way, this was just one shipment. The whole machine takes several shipments of 747, okay? So this was just one of the shipments. This was the frame of the tool. This is this is the illuminator, and this is where the lens sits. Okay, the optics sits. Okay, this is the optics, and this is the illuminator, which is still. This is where the illuminator sits. It's still not in there yet, and the wafer stage is not in there yet. And there's a big hole here, and this is where the wafer stage slides in. So in this one, you only see the EUV optics, the 0.33 NA optics. The illuminator is not there yet, and then this is. Sorry, I misspoke. 0.55 NA optics. Okay, this is a high NA machine. The illuminator is not in there yet, and this is part of the light source, the vessel. Okay, sitting right here. The CO2, the gigantic CO2 laser is in the subfab downstairs. Okay, so now what happened here in Europe? In Europe, we have the joint lab with imec. imec is now a partner of Purdue, and this is where we print wafers ourselves and also print wafers for our customers. And the customers can also come and use this machine. This is the same machine as the one I just showed in the video. The towel track made it to the EUV scanner, and this is the ancillary room, okay? So this is the high-NA lab at ASML, but it's a joint lab. It's actually run by imec, okay? Joint lab with imec. So let me show you some, quickly show you some images. This is a DRAM pattern. This is a DRAM storage cell, but it also has the periphery circuits, right? The sense amplifiers and the subword drivers. And this is the storage node pad underneath the storage node. So not only does DRAM, okay, so if we try to print this with low NA, you get defects because this is really at the resolution limit of the low NA. Okay, with high NA, no problem. The pitch can even go below pitch 28. So this was pitch 32, pitch 28. But as you know, DRAM also has the other tone. This is the thing I just showed. But for the storage nodes, storage holes, we actually have to print contact holes. So this is the positive tone, negative tone. So we need both tones, okay, for printing the DRAM cells. And of course, you know, depth of focus is a concern for high NA if you just print it with a conventional illuminator, but you can always do something to the illuminator, and you can also control the shape of the pupil, which I don't have time to go into, and then you can improve the depth of focus, okay, almost by 2x. Okay, but that was for DRAM. You can also print logic circuits of tomorrow. This is a metal layer with a pitch of 19, right? This is the contact hole layers with a pitch of 30. And here we talk about center to center distance is the same as pitch. So the CD size is nominally 15. And this is after imaging, and this is after etching. Okay, so this is where things are as we speak. So where do we go from here? Right, I got 5 minutes to. First, let me remind you this famous formula, K1 lambda over NA, and we need to lower K1. The K1 is not close to 0.25 yet. In optical lithography, it is already quite close to 0.25, but not in EUV yet, okay? So we need to work on that, and that's a lithographer's job, is to lower K1, right? Of course, lambda remains at 13.5. What we're going to do at ASML is to put common platform for all exposure tools. I'll explain this later. And then what's the ultimate limit, right? So let's go. Now, a semiconductor manufacturer is going to continue to drive transistor shrink. Of course, we don't shrink as fast as once upon a time. For example, this was the 40 nanometer node, 40 to 28 to 23. As you can see, the slope, the metal pitch shrinkage, right, high. The slope is now a lot smaller, but it's not zero, right? It continues, the slope continues to go down at a slower pace, of course, right? So we still need lithography exposure tools in this area, right? But things get a bit murky, so that's why you have an uncertainty bandwidth here. But it's clear, in the near future, it's clear, it's continued to drive down. Right now we're at 23, it'll be 22, 21, 18, and 17. So, and then, of course, for this regime, we are looking at a numerical aperture even higher than 0.55. We call it the hyper-NA, right? The numerical aperture would be 0.75, and this is, it's on our roadmap, okay? All right, so for 0.55, we can actually print 8 nanometer half pitch. This will be corresponding to a K1 of 0.33, dense lines and spaces, right? So with a dipole illuminator. Of course, they are not good enough for production, okay? But the raw capability is there, okay? So now, this slide was animated, but in the interest of time, I made this thing in one go. So what do we have to, what happens when you image near the resolution limit? You come in with a light, you get diffraction orders. Okay, let's assume this mass pattern is a grating, right? You get grating diffractions, but you only collect the 0th order and the 1st order. All the high orders go out the lens, right? Not collected, which means your image will be sinusoidal. The sinusoidal image is there, but the sinusoidal image also has various qualities. So if you do the analysis, and this is what you get. We actually never expose the mask with only one pole. We always have the other pole, so this is called a dipole illumination, trying to get the best contrast. But the contrast itself, in the end, is marred by these factors in this expression, okay? You would like to get an expression like this, okay? This will give you a contrast of 1, the best contrast, right? You look at this expression. P is the pitch, okay? But in reality, what you get is this one. Now, all these factors work together to lower your contrast. So what do you want to do? You want to have a better resist so that this sigma is smaller. So this exponential factor stays close to 1. You want to have narrow dipoles. You don't want to have these fat ones. You want to have the narrow dipoles so that the depth of focus is higher, better, and then The contrast is higher when you are out of focus. And you want to reduce the mass 3D effect. What happens is that these diffraction order, the zeroth order and the first order, they don't have the same phase. So what happens when you don't have the same phase? Well, the pattern shifts laterally, okay, on wafer. You don't want that. You don't want that. Of course, you come in with the other pole and it shifts the other way. So in the end, the wafer is still set, the pattern is still centered. However, the contrast is lowered, right? And it's represented by this factor here. Okay, so you want to minimize that, right? You want to do all these things to improve your contrast. Okay, so let me just give you a demo. One thing, this is a fat dipole. You can see this is the depth of focus. If you go to a thin dipole, your depth of focus is increased, right? That's just one demonstration. Okay, now the last example I'm going to give you is this tip-to-tip spacing. We do, again, I'm showing this pitch 19 nanometer logic metal layer, okay? And what's tip-to-tip spacing? You can see these metal lines, they butt against each other, right? Why? Because there are two contact holes sitting underneath them, okay? You put metal lines on the top. Of course, you have to leave some enclosure. And then this is tip-to-tip. Of course, you want the tip-to-tip to be as small as possible because then the contact holes can be squeezed closer together, right? Okay, so this is again from imec. Now, this actually, this basically 28, 24, 22, 20. This metal pitch gets smaller and smaller. And what happens is that when the metal pitch gets smaller and smaller, the gap, the tip-to-tip, they pull apart. That means the tip-to-tip gets bigger and bigger and bigger. This is just the physics. I'll tell you the physics on the next slide. So the rule of thumb formula is this formula. Okay. Basically, as you can see, experimentally, the tip-to-tip spacing gets bigger and bigger and bigger. It doesn't matter how you design it on a mask, right? On a wafer, it gets bigger and bigger and bigger. So why is that? Okay. Now, some Fourier optics. Okay. I want to get you to be excited about learning Fourier optics. This is the situation. This is a stripped down version of the metal zero layer, very nicely spaced grating with a pitch and with a gap. How close can a gap be, right? So first, you decompose this. This problem is the same as an infinite grating times a strip, isolated strip, an isolated space, okay, with a width g, okay? This times that is equal to that, okay? So you illuminate this structure with a dipole, okay? Now, in the Fourier space, I have no time to go through this physics of Fourier space. Every lens has a Fourier space. The Fourier space is at the back focal plane. Okay, Fourier space, this is what happens, right? This grating would give you the two bars, just like the illuminator. And then this thing, the Fourier transform of this guy rides on these bars, okay? And this is the mathematical expression. This is a sinc function. The sinc function is good. The smaller the g is, what happens? The bigger the sinc function, right? So in order to form the spacing, a large part of the sinc function needs to be captured by this numerical aperture circle. If they fall outside, you can't form the spacing. The two lines will be touching. And then what happens in reality is you have to pull them apart in order to have the spacing. Okay. So now, what do you do? And this is where this formula came from. If you do some simple analysis. So what do we do in reality is we put some light in the middle, and what does that do? That gives you a spot in the Fourier space, also in the middle, and then the sinc function rides on top of it, as you can see, because it's wider here. Okay, so more of the sinc function can be enclosed in this NA aperture, so that your resolution on the wafer becomes better. That meaning you can get to a narrower spacing. Okay, and this is some results that we my guys collaborated with imec and Lam. We used a Lam dry photoresist, and you can see that the best results is here. Okay, you had a tip-to-tip local CD uniformity of 3 nanometers at a tip-to-tip spacing of close to 13 nanometer. Okay, and we did that with a new EUV mask, which had a low-end absorber translating to a smaller mass 3D effect. And we had the better photoresist. All right, we used the metal photoresist with a smaller sigma. Okay, less blur. And then, of course, Lam says we use the best recipe. We don't know what this recipe is, but it's the best recipe from Lam. All right, so this is my last example. Okay, can we do better? Can we do better than that? Well, let's look at a simpler problem. I just want to have another 5 minutes. Okay, so this is a simpler problem. It's not a 20 nanometer pitch thing. Let's have a very large pitch, and you'll try to print this gap. How small can you print it? Okay, you do some simulation, and you get this. Right? You do some simple aerial image calculation. It really doesn't matter what kind of a phase shift you put on this bar. This is the kind of a number you get. This gap is 0.6 lambda over NA. Can't get any smaller. Can you get smaller than that? Yes. You get rid of the bar. You make this whole thing transparent, but you introduce a phase shift right here, okay, where the ball was. And if you do that, because the electric field has to go from 1 to -1, in this case I use the minus square root of t, but you could just think of it as totally transparent, -1. Because it has to go through 0, you force the intensity down to 0. Of course, intensity gets flipped, it comes back again, but you have to go through 0, okay? And then if you do the simulation, look at this. A much smaller gap can be formed by using a phase edge. Phase edges are very powerful means to get you an isolated small feature, okay? And what is the size? 0.26 lambda over NA, almost close to 0.25, okay? A lot smaller than that. Can you get it, okay, that translates to, with a high NA lens at EUV wavelength, a gap of 6.4 nanometer, right? Much smaller than 13 that I showed on the previous slide. Of course, this is a simpler case. This is not a 20 nanometer pitch, okay? Well, actually, something like that was not invented by me. It was understood by this guy called Ernst Abbe more than 100 years ago. In 1910, 5 years after his death, a book was published because the students were taking notes in his class, and they published this book. This book was translated to English 2 years ago by myself and my friend Martin Burkhardt from German. And look at this. This was in the book. Right here. Same as this. Okay? And can you do it in EUV? Yes, you can, at least in simulation. Look at this. 5.53 nanometers, okay? At a pitch of 42 nanometers using dipole illumination. Yes, you can, but you have to make a mask, make a phase mask, okay? I have to tell you this next time. All right, now, this is how to lower K1, okay? Now what are you going to do? What is ASML going to do? ASML going to continue to improve our machines. We're at 3800E. We will have the 3800F, the 4200G. The 0.3 NA line is going to continue, and also the 0.55 NA. We're done with the 5000. We're now shipping the 5200s, okay, and then 5400C, 5400D, and then so on. In the future, what happens is that we're going to have the common platform to house both the low NA and the high NA. And this is today, and then in the future, we're going to have one platform, but two different lenses, okay? 0.33 and 0.55, and eventually we'll have the 0.75. They all gonna go into the same housing, okay? That's our roadmap. Okay, so last question. How small can you realize with 13.5 EUV lithography? Okay, now let's look at it using interferometric lithography. Interferometric lithography is just the two beams, okay, two optical beams with no lens, so no mass 3D effect, but it illustrates the point. These results were made by Paul Scherrer Institute in Switzerland using interferometric lithography. As you can see that they can go all the way down to half pitch 5, which means the pitch is 10 nanometers, using a very simple setup. This is a one-armed interferometric lithography, okay? Now, only the center lines are good, and the outside lines are fuzzed out because this light has very short temporal coherence, okay? But if you were to use this setup, then all these lines will be good because the optical distance, the optical path will be the same, okay? So that's it, folks. This is my last slide. We have a bright future, okay? Thank you very much.